In this section, we are going to study the linearizations and the local stabilities. We consider the general differential equations near the critical point of x sub c. So we only examine local stability of a critical point. So we replace the right hand side of the equations with the linear terms as these equations. So this is the exact form of the equation. X prime equals gx. And the gx is approximated with a linear term of the ax minus x sub c. X sub c is a critical point. So I'd like to show you the examples. X is a function of t. So x prime is given by the fx. So critical point is given by the x equal x sub c. So if you substitute x equal x sub c, fx sub c have to be 0 because x sub c prime is gonna be 0. Fx sub c equals 0. Then a function of f is approximated using the linear equations. Then equations, you can substitute these equations to the right hand side of the original differential equations. Equation is transformed to this equation. Then we'd like to solve this equation. We are going to consider the stability of a critical point. So we linearize nonlinear first order differential equations as x prime equals f prime at x equals x sub c. So this is a constant quantity times x minus x sub c. So if f prime at x sub c is a negative quantity, then x equals x sub c is asymptotically stable critical point. So this corresponds to the red curves. So this is x prime is a negative quantity. So if we consider some points close to the x sub c, the x prime is a negative. So it's decreasing and approaching to the x sub c. Because this point is larger than the x sub c, x minus x sub c is a positive quantities. So this is positive quantities. So this is positive quantities. F prime is a negative quantity. This is going to be negative quantities and approaching to the x sub c. So x sub c is a stable critical point. On the other hand, if the f prime is a positive quantities, then f prime is positive. So positive times positive. So this point is x prime is a positive quantities. So if you start here, the x prime is positive. So x value is increasing, moving away from the x sub c. Then we can find out that this is an unstable critical point. So by finding the sign of the f prime, we could find out the stable critical point or unstable critical point. Now we'd like to consider the plane systems. In a plane system, we have two dependent variables, x and y. First of all, it's better to linearize the equations. So when we consider plane autonomous system near a critical point of x sub c and y sub c, the equation approximated with this equation. So p xy is round p round x sub c, x y sub c times x minus x sub c plus round p round y, x sub c, y sub c, y minus y sub c. Actually, we use a p x sub c, y sub c equals 0. Also q x sub c, y sub c equals 0. Then we can expand the capital qxy is a very similar way with a capital P's. So round q round x times x minus x sub c plus round q round y, y minus y sub c. Then we combine this equation using the matrix. So x prime y prime equal round p round x, round p round y, round q round x, round q round y times x minus x sub c, y minus y sub c. Then we'd like to consider the stability of the plane systems. We introduce a new dependent variables given by capital H equal x minus x sub c, y minus y sub c. Then from this equation, you can find that the x prime equal x prime y primes, because x sub c prime y sub c prime equals 0. So this equation is transformed into the new equation of the h prime equal ah. This matrix is A. Then we can use a method we have obtained when we studied linear plane autonomous systems. So when the eigenvalue of A has a negative real part, then x sub c becomes asymptotically stable. On the other hand, when the eigenvalues of A has a positive real part, then x sub c becomes unstable critical point. So we could find the local stability of a critical point. So as an example, we consider the nonlinear pendulums. Some object with a mass of the m is attached to the strings. The length of the strings is lowercase of the l. Then we'd like to write down the equations of motions. So ml times the second derivative of the theta with respect to t. So this corresponds to the a, accelerations. So length of the string is L and the theta is the angles. So actually this length is given by the L thetas. This is the length of the S. So from this S, you can calculate the velocities, ds over dt's. It becomes L times L is a constant quantity, so d theta dt's. And the acceleration is a dv dt. You can substitute this v into this equations, then it becomes L, second derivative of theta with respect to t. So acceleration is L times the second derivative theta with respect to t. And the force acting on this object is the tension force and gravities. But gravity is only important quantity to change the speed of the object attached to the strings. Gravitational force acting on this object perpendicular direction with respect to the string is a minus mg sine theta. So this right hand side of the equation is a force acting on the object by the gravities. So this equation, by dividing by the ml, this is second derivatives of theta with respect to t is going to be minus g over l sine theta. This is a higher order differential equation, second order differential equation. So we'd like to introduce a new variable y. Y is given by the first derivative of theta with respect to t. So second derivative of theta with respect to t becomes a y prime. Y prime equal minus g over l sine theta. So we consider these two equations. So equation becomes this one. So to find the critical point, we consider that this right hand side is equal to the 0. So y equals 0, y sub c equals 0. So from the second equation, sine theta equals 0. To satisfy the sine theta equals 0, theta sub c becomes an integer multiple of pi. So plus minus k times pi. K is an integer. Once we find the critical point, we'd like to consider the stability of each critical point. Matrix of A can be calculated. Round P round theta, round P round y, round Q round theta, round Q round y, and at the point of the critical point. By substituting this critical point into this P is a y, so derivative of theta 0. And derivative of p with respect to y becomes 1. Derivative of q with respect to theta becomes this becomes minus g over l cosine theta. Then you can substitute theta is a plus minus k pi. So it becomes minus 1 to the k plus 1 times g over l. And the round q is not a function of y, so derivative becomes 0. So from the matrix of A's, you can calculate tau equals 0. And also you could calculate the delta is a g over l minus 1 to the k. So when the k is 2i's, even numbers, then delta becomes a positive quantities. Delta is a positive quantities, it becomes stable centers. When the k is 2i plus 1, delta is a negative quantities. Because of the delta is a negative quantities, it becomes a saddle point. So it becomes an unstable critical point. Okay, so I explained one of the examples of the nonlinear systems. So in these chapters, we study the plane autonomous systems and the stability of such systems, even if we encountered nonlinear plane autonomous systems. We could linearize the equations and we could discuss the local stability of each critical point. Okay, this is the end of this chapter.